So I wanted these tubes. I was initially interested in the Russian equivalent of these, the GU17, but anyways I found already here in Italy on eBay an auction about two of these tubes, the QQE03 12 made by Philips, so I bought them. And to celebrate the purchase I made an oscillator with one of the tubes. Yes, another one, lol. And this oscillator runs at like 123 MHz and it's decently refined in terms of component values. It's the highest that I ever made in terms of frequency, and it's a push-pull topology. For the resonant coil, I'm using here 3 turns of copper wire, and you usually make a bow of wire, just a bow for these frequencies, but instead I wanted some turns and a shrunk coil to ignite easily small gas tubes in it. There's also a small choke coil for the B plus of the circuit here, and it is made with a few turns and a ferrite to increase the inductance. But anyways, this choke coil doesn't need to do anything hard, anything special, and it's made with a fairly small, fairly short copper wire, shorter than the quarter lambda of the resonant frequency of this thing. And anyways, I power this oscillator at like 300 volts DC, or maybe a bit more. That is white-in specs. For the feedback capacitors, I made a sort of specialty, because I needed 2 capacitors of like 3 picofarads, but they must be high performance. So to make high performance capacitors, I made air capacitors. And I wanted to make a voltage divider from the anode of the tube to the opposite grid. And to have a voltage divider with a ratio of 3, you need a capacitor of like 3 picofarads, because the each grid one is 6 picofarad of stray capacitance. And I made these structures with the copper sheets bent like an U, and these are slid the one inside the other, 4 pieces in total. And they have a distance of like 2 millimeters, so they are fairly high voltage. And these are sustained with some brass pillars, small brass pillars, and soldered on a piece of copper clad board with the middle copper removed to insulate it, obviously. And they come up to be high performance, obviously, but maybe a bit high in inductance, because their pins are bent to connect it to the socket of the tube, but who cares at the end? And here's the schematic. So let's try this thing. Now the cathode is hot. Let's turn off the light to see it better. Sadly, you can't see exactly the cathode. Sorry for the focus. There are too many grids. Anyways, now my scope is on with the maximum fastest time base possible. I have the probe here, put at 1x magnetically coupled. Let's give like 30 milliamperes. I don't know, like 200 volts. Let's put the probe here. Let's see. We have a frequency of almost 124 megahertz. I'm playing with the probe. Okay, now some tricks. I have this circular tube here, fluorescent tube, pretty classic, nothing special. The tube is ready. Let's give almost 300 volts of supply with a current consumption of above 50 milliamperes. And let's see on the coil, on the resonant coil, and it turns on, but with 2 levels of brightness. You can see better on my computer monitor the difference in brightness. So basically in this case now it's just the electric field that ionizes the gas. When it's like this instead, it's inductively coupled plasma. So basically the trick is that the electric field ionizes the gas inside the tube, and when the gas is ionized, it can receive power inductively because the gas inside the tube makes like some sort of shorted turn, and it can receive power magnetically, and it's much higher than the power received with the electric field. Okay, same thing with this CFL light bulb, just a tube here. Let's give again the B plus supply, and let's see. And it has two levels of brightness with a sudden change, and probably this inductively coupled plasma is eased by the high frequency. Also, my multimeter jumps in power up to like 100 milliamperes when there is ECP. Okay, now this again B plus. Let's stick it in here. That's the tube camera. Pop, pop, and I can let the ECP travel along the tube. Pop, pop. You can see my multimeter. Let's see the range. Not much. Near the anodes. It's like, I don't know, 10 centimeters. Not much. Okay, now this mercury vapor lamp. The tube is ready. Let's give again the almost 300 volts. Let's stick it in here. It turns on at some point while heating up. Okay. And it starts making much more light. Phew, ozone. It's very bright. The exposure is very low right now, huh? Pop, pop, pop. Ooh, it's so bright under the naked eye. It burns my flesh. A burning love of ultraviolets. Okay, now for the Tesla coil, I have here this coil put inside the tuning coil, and it's an inductor, let's say, of like 19 turns of 0.5 millimeters copper wire, wound over like 1 centimeter, and it came up to be 1 microhenry, and it has calculated 1 picofarad of shunt capacitance, and it's fairly hard to tune this thing because you have to match the two resonant frequencies of the output coil and the oscillator. Anyways, I did a mixture of my experience, online calculators, inductance and capacitance calculator, resonant calculators, Tesla coil calculators, and I kinda hit the spot almost immediately. But it's very sensitive. Anything you change on the coil makes it not work at all. So also I couldn't use a small output electrode. I had to use the original copper wire 0.5 millimeters, because if I put a small top load on this thing, it goes out of tuning and it doesn't work anymore. Anyways, the output here, sorry, it's not impressive. It's just a really small flame. Okay, now I have the supply transformer under my variac put at like 260 volts SC, so it's more than 300 volts, like 330 volts of supply voltage. Now the cathode is hot, it's also driven a bit harder because of the higher power on the power transformer, on the supply transformer. Okay, I have here this screwdriver to spark the output. Let's give the B plus and let's see. Okay, and off. It's already smoking because the output electrode is too weak because I couldn't put a stronger electrode, sorry, but let's try again. Okay, power and output. Okay, and that's enough for my test. So thank you for having watched my video, and here's the whole family reunited for the final picture. Anyways, as always, if there are updates for this project, you'll find them below in the description of the video. So at this point, I think goodbye for now.